Hey everybody, in this video we're going to be reviewing Unit 13, which is about sequences and series. For your warm-up, I'd like you to give an example of each of these three things. First, an arithmetic recursive formula, a geometric sequence, and then a series that has a common ratio of 1/3. Give this video a pause, make your best guess, and see what questions you have. All right, so starting off with a recursive formula. A recursive formula is a formula that allows us to generate the next term in a sequence. So we're only able to find one additional term at a time. Okay, there's two parts to a recursive formula. The first part is the first term, okay, and we use U1 to describe the first term. And the second part of the recursive formula is our pattern. And again, our pattern is always about how do we get the next item or the next term in this sequence. So in the pattern portion, we're going to describe what happens to that previous term. U(n minus 1, that's the previous term. Okay, and then we need the pattern after it. Since we are being asked to write one for an arithmetic scenario, our pattern needs to involve adding or subtracting, which really is adding. We're just adding a negative number. So I would need any original value, like 5, U(1 = 5, that's the first term, and then any pattern that involves addition or subtraction. So for example, U(n minus 1 + 3. Or -5, or +7, or -52, you get the idea. But we need two parts to this recursive formula. Next up is a geometric sequence, and we have to remember that a sequence is a list of items, a list of terms. So we're going to need to make a list with commas in between. A geometric sequence is a list that has a pattern with multiplying. Okay, and we can multiply by a whole number or a fraction or even a value with a decimal. So I'm going to just pick any arbitrary starting value. I'm going to make it 2, and I'm going to make this pattern multiplying by 4. So if I multiply by 4, my next value is 8. If I multiply by 4, then I get 32, and then I can just write some dots to show that this list will continue. To show that the pattern is geometric, we need at least 3 terms. If I only did 2 terms, I wouldn't know if that pattern was adding 6 or if it was multiplying by 4. So that third term clarifies whether it's arithmetic or geometric. Next up, we're going to write a series that has a common ratio of 1/3. Now, a series is different than a sequence because a series is a summation, meaning that we need plus signs in between our terms. Okay? A common ratio of 1/3 means that this is also going to be a geometric scenario, like the sequence before it. Now it's a series. And that common ratio tells us what we're going to multiply by. So we're going to multiply by 1/3. So I'm going to pick a starting value that's going to be a multiple of 3, just to make it a little bit easier to have that common ratio of 1/3. So I'm going to start out with 27. Okay, and if I multiply that by 1/3, same thing as dividing by 3, I'm going to get 9. And then you can see I changed from the comma to the plus sign in between. Okay, so multiplying by 1/3 gives me 9. I need one more value in this series to show that it is geometric and not arithmetic. If I multiply that by 1/3, I get 3. Right? I could even go further, multiply by 1/3 one more time, I would get 1, but I think 4 terms is enough. You need at least 3. There is an example of a geometric series that has a common ratio of 1/3. One last follow-up comment, that pattern in a geometric sequence or series, we call that value the common ratio. Multiplying by 1/3, multiplying by 4, those would be common ratios. In an arithmetic scenario, whether it's an arithmetic sequence or an arithmetic series, the value that's getting added each time, we call that the common difference. So there's a quick overview of the difference between recursive formulas, sequences, and series, as well as the difference between arithmetic and geometric scenarios. We could be asked to write these things, we could be asked to analyze these things, or we could be asked to find specific values, like a specific term or a sum of terms, which we'll look at more. Here are the formulas that we're going to be given on the summative. We just need to know what these formulas allow us to find so that we can decide when we want to use them, as well as what these variables represent so we know what values to plug into the formulas. So starting with the first row, the u with the subscript of n, u sub n. We have one for arithmetic and one for geometric. These allow us to find specific terms. Okay, they're sometimes called explicit formulas. They allow us to jump to any term we want. We can jump to any number in the list. We don't have to generate the full list to find the term that we're most interested in. So this might be finding the 28th term or the 30th term in our list. We're going to need to know if that list is a geometric list or arithmetic list in order to find it. We can also use these term finder formulas in series as well, but they don't allow us to find a sum. It's just one specific number in the list. To find a summation, we're going to have to use one of the formulas that has an S in it. Okay, so the next row, S sub n, there's one for both arithmetic and geometric. These are to find the sum of n terms. So maybe you want to find the sum of 50 terms or 32 terms. Okay, again, different for arithmetic and geometric, so we got to make sure that we analyze our series to know what type of patterns we have. The last one, S with the infinity underneath, this is an infinite sum, which seems crazy, but it is possible to calculate an infinite sum, a sum of infinite numbers. But it's only possible if the situation is geometric, and if that common ratio is between -1 and +1. Okay, only then can we find an infinite sum. All right, within these formulas, we also need to know what these letters represent. So you see in every single formula, u sub 1. That's the u with the subscript of 1. This is referring to the first term in that sequence or series. We also see n a lot. Okay, n refers to the number of terms that we have. So maybe it's the term number that we're looking for, or maybe it's how many terms we're adding up together. Then depending on if it's arithmetic or geometric, we might see the variable r or the variable d. Okay, in arithmetic, the variable d is the common difference, so that's the number being added each time. If the numbers are going down, remember that common difference is going to be negative. Okay, and lastly, in the geometric formulas, you see this variable r. Sometimes it shows up more than once. Okay, and the r represents the common ratio. We always want to express the common ratio as a multiplication factor. So instead of thinking of division, we're going to think of multiplying by a fraction. So if our pattern is division by 2, we would rephrase that as a common ratio of 1/2, because we know dividing by 2 is the same as multiplying by 1/2. All right, a quick check-in with yourself. What would be the difference between u sub 11 and s sub 11? See if you can pick out what formulas you would use and also what your answer would represent. Then see if you can calculate both U sub 11 and S sub 11. Give this video a pause, analyze the differences, make some calculations, and see what questions you have. All right, so before I get into the differences, let's just look at what we have. We have a series, and I know it's a series because of the plus sign. Okay, if it was a sequence, it would be a list, and we would have a comma. Next, I'm going to look at the pattern. 1, 2, 4, 8. So I see those values are getting bigger. So since it's increasing, it must be either a pattern of addition or a pattern of multiplication. Okay, and if it was addition, let's see. The first round, I'd have a common difference of 1, but then the second round, I'd have a common difference of 2, and the third round, I'd have a common difference of 4. Since that pattern isn't consistent, I know the pattern isn't going to be addition, okay, which means this isn't an arithmetic series. Thinking about multiplication, the first round, the common ratio would be 2. 1 times 2 gives me 2, and I can see that pattern is consistent. The next round, 2 times 2 gives me 4, then 4 times 2 gives me 8. So I know that this series is geometric, and I know that the common ratio is 2. So what's the difference between U sub 11 and S sub 11? With the U, I'm looking at the specific term. So this is asking me to find the 11th term. Versus S sub 11, this is asking me to find the total of the 11 terms. So adding up the sum of those first 11 terms. So I know I'm going to use different formulas, but I'm going to pick the 2 formulas that fall under the geometric category. Again, you do not need to memorize these formulas. For the 11th term, I would use the formula with the U that falls under the geometric column, which says take the first term times the common ratio to the power of n minus 1. That formula is definitely a little bit more straightforward. I would have all the information that I need, the first term, the common ratio, and the number of terms, n would be 11 in this case. This would be an R2 level question. The summation formula is much more complicated. To find the sum of 11 terms, we're going to take the first term times the ratio to the power of n minus 1. Okay, and the minus 1 is not in the exponent position. Only n is in the exponent. And then we're going to divide that by the common ratio minus 1. Relatively straightforward because we do have all of the information that we need, but it's a much more complicated formula, which makes it an R3 level. Now we're going to take a look at a word scenario and kind of convert it into a sequence or a series and analyze that scenario so that we can calculate some specific values of interest. So this scenario says that a lemonade stand is set up at a park. In the first hour, the lemonade stand makes a total profit of $10. Each hour after that, the profits are $6 more than the previous hour. So first, before I look at the questions, I'm just going to write out what this pattern is and what those terms would be. So my first term is 10. That's how much money is made in the first hour. The second hour, the profit needs to increase by $6. So that means in the second hour, the profits are 16. In the third hour, if I add 6, the profits would be 22, then 28, and I could continue on assuming that the lemonade stand continues with this pattern. So, first question is, how much money will the lemonade stand make during their fourth hour? Okay, I have 2 different options for this. I could use the specific term finder, and I could plug in my values, or I could just use the pattern and find that 4th term. Since 4 isn't a very high number, it's not very far into the list, I would say that just finding that 4th value without the term finder formula would probably be a more efficient method. Okay, so I've already actually written out that 4th term, and I found that they would make $28 in that 4th hour. The second question asks, when would the stand make at least $45 an hour? So I want to know what would be the time, the hour, that they would reach this value at. Now I could approach it the same way, continue my list and find when those numbers get bigger than 45, or I could use the specific term finder formula. So that's what I'm going to do this time. I know that I want that specific term to be 45, but I don't know when that will be. I want to figure out n. So first I need to figure out what type of scenario is this. And since our pattern was adding 6, I know that this is an arithmetic scenario. And I know that that common difference is 6. I also know that the first term is 10, and that I'm trying to figure out the value of n for when my specific terms reach 45. So I'm going to go back to my formula list, and I'm going to pick out the specific term formula for arithmetic sequences and series. And it looks like this. I'm going to plug in all the information that I know and then solve it like an equation for n. So my total is 45. The first term is 10. I don't know n, so I'm going to leave that as n in the formula. And the common difference is 6. Okay, there's multiple ways that you could approach this solving scenario, but we want to make sure that we use reverse PEMDAS order. So if it's helpful to you, write out PEMDAS off to the side and make sure that you're going backwards. So I'm going to start with adding and subtracting. I'm going to subtract 10 from both sides. I get 35 is equal to n minus 1 times 6. Then I'm going to do division. So I'm going to divide both sides by 6. And I'm going to get a decimal value here because 35 isn't divisible by 6. So I'm going to use my calculator to help me. Okay, and I get 5.83 is equal to n minus 1. Then I'm going to add 1 to both sides. I'm now in the parentheses stage since I've gotten down to that parentheses of n minus 1. And I get 6.83. Now we can't have a decimal value because n is the term number. So the n value has to be a whole number. I can either have the 6th term or the 7th term, but I can't have term number 6.83. So if I think about the 6th term, I'm not going to have quite enough money to get to $45. So I'm going to round up. Okay, and the 7th term is going to be the first time that I have at least $45. It'll be a little bit bigger than 45, but the 6th term wouldn't have given me enough money to reach that amount. Here's what else is going to be on this unit summative. Okay, so recursive formulas, like we talked about in the warm-up, making sure that we understand what a recursive formula looks like, that there are 2 parts to that recursive formula. We have the first term and the pattern. Always telling us how do we get one step further down that list. Okay, so we could use a recursive formula that's already written for us to find a pattern and identify if a scenario is arithmetic or geometric. We could write out the first few terms, or we could go backwards and we could write a recursive formula for an arithmetic or geometric sequence. The next topic is finding a specific term. So using a pattern to notice if it's arithmetic or geometric, and then using those formulas to find a specific term in that list. So maybe the 27th term or U sub 15. Remember that if it's given to us in that notation, U sub 15, that's referring to the 15th term in the list. So our n value would be 15. Next up is the summation formulas. So that's where we have an S. Be careful, it could be an infinite sum or a finite sum. So analyzing series for the patterns, if it's arithmetic or geometric, and then using those formulas to find the sum. Just like with the specific terms, if you have S sub 15, it's referring to the sum of 15 terms. So that subscript might give you a little bit of information. That would tell you the end value is 15. Next up is the applications. Those would be like the word problems we were just talking about on the previous slide, the lemonade stand, figuring out if something is arithmetic or geometric based off of the description, and then using the information to find specific values, like how much will the lemonade stand make in the 5th hour, or when will the lemonade stand make at least $45. Hey, and the last one is puzzles. So using our formulas with partial information to find missing values. This might look something like the sum of an arithmetic scenario is 250. And we know that there are 28 terms, and we know that the first term is 10. We want to know what's the common difference. All right, that could be an example of this puzzle where we have some information, but it's not complete. We need to find the missing information. I just made these numbers up, so if you try to solve that, I don't know if it's going to work or not. That summarizes Unit 13. Make sure that you practice all of these different topics. There's lots of ways to combine these skills, and we want to make sure that we're feeling confident with them all.